Hi, this is Priyanka Kumari, and today I'm going to talk about common parallel programming problems and its solution. These are common problems: too many threads, data races, deadlocks, and live logs, heavily contented logs, non-blocking algorithms. Few more things which will be covered as a common problem is thread safe functions and libraries, memory issues, cache related issues, pipeline stalls, and data organization. Too many threads. Little threading is good and many will be great is not always true. Excessive threading can degrade the performance. There are two types of impacts of excessive threads. First, too little work per thread. It will lead overhead of starting and maintaining dominance. Excessive contention for hardware resources. This means OS uses round robin scheduling for fair scheduling. This may result in excessive context switching overhead, thrashing at virtual memory level. The solution for this too many thread, we have options. The first option is limit the number of runnable threads to the number of hardware threads and possibly limit it to the number of outer level caches. The second option is we should never ever hardcode the number of threads. Leave it as tuning parameters. A helpful organizing principle is to separate compute threads from IO threads. We can do it using several ways. First is OpenMP, second is thread pooling, and third is experts may wish to write their own task scheduler. Writing own task scheduler will be a better solution. Data races, deadlocks, and live logs. First point is race condition. How it arises due to asynchronous access to shared data, and program results are non-deterministic. How it happens when relative timing of threads means one thread will take specific time in first execution and second execution it takes a different time, so this will lead a non-deterministic value which is not a good programming. This can be handled using locking race among asynchronous threads. In this example you can see there are two separate threads trying to add to shared variable x, which has an initial value of 0. Depending upon the relative speeds of the threads, the final value of x can be 1, 2, or 3, which is not a good programming. But the same race can be hidden by language syntax in a variety of ways, as shown by the example in this figure. So we can see compiler expand plus equal to into separate read and write of x, and subscript of I and j might be equal, and pointers of p and q might point to the same location, and foo might be adding its argument to a hidden shared variable. Even at the instruction level, the hardware expands and updates of ADDIE into separate reads and writes. A higher level race condition example. In this example, we can see that synchronization at too low level also leads this problem. Not only when it is unsynchronized. So race condition occurs in this example. The intent is to use a list to represent a set of keys. Each key should be in the list at most once. Even if the individual list operations have safeguards against the races, the combination suffers a higher level race. If two threads both attempt to insert the same key at the same time, they may simultaneously determine that the key is not in the list, and then both would insert the key. What is needed is a lock that protects not just the list but also protects the invariant, so no key occurs twice in the list. Locking is the solution for race condition. But when we put locks, incorrect locking leads us to deadlock situation. As we can see in deadlock, a cyclic dependency happens that stops forward progress by any of the. In this deadlock example, you can see that thread 1 has acquired a lock on A, thread 2 has acquired a lock on B. Each thread is trying to acquire the lock and acquire the other lock, so neither thread can be proceed. Conditions for a deadlock. Deadlock can occur only if all the four conditions are true. First is access to each resource is exclusive. A thread is allowed to hold one resource requesting another. Third is no thread is willing to relinquish a resource that it has acquired. And the fourth one, there is a cycle of threads trying to acquire resources where each resource is held by one thread and requested by another. Best way to avoid deadlock is to replicate a resource that requires exclusive access so that each thread can have its own private copy. If replication cannot be done, that is, in such cases where there really must be only a single copy of the resources, common wisdom is to always acquire the resources, that is lock, in the same order. The ordering rules that are most convenient depend upon the specific situation. If there is no obvious ordering of logs, a solution is to sort the logs by address. This approach requires that a thread know all logs that it needs to acquire before it acquires any of them. As you can see in this example, how logs ordered by their addresses. The last solution is prevention of deadlock. The way of preventing deadlock is for a thread to give up its claim on a resource if it cannot acquire the other resources. For this purpose, mutex often have some kind of try and lock routine that allows a thread to attempt to acquire a lock and give up if it cannot be acquired. And this approach is useful in a scenario where sorting on the locks is impractical. Live lock. Live lock occurs when thread continuously conflict with each other and back off. No thread make any progress. And to solution this live lock problem, back off with release of acquired locks to allow at least one thread to make progress. As you can see in this example, try and back off logic, it applies exponential back off to avoid live lock. If a thread cannot acquire all logs that it needs, it releases any that it acquires and waits for a random amount of time. The random time is chosen from an interval that doubles each time the thread backs off. Heavily contested locks. Locks ensures correctness by preventing race condition and by preventing deadlocks, but performance will be impacted. These are below conditions which will impact the performance. First, when lock becomes heavily contested among threads. Second, threads try to acquire the lock at the rate faster than the rate at which a thread can execute the corresponding critical section. Third is, if a thread falls asleep, all threads have to wait for priority inversion. Some threading implementation allow threads to have priority. When there are not enough hardware threads to run all software threads, the higher priority software threads get preference. For example, in this priority inversion scenario, what happens in our analogy with software threads are cars and hardware threads are drivers. Three cars are shown, but there is only a single driver. So a low priority car has acquired a lock. So it can cross a single lane. Critical section is bridge. Behind it waits a high priority car. But because the high priority car is blocked, the driver is attending the highest priority, that is runnable car, which is the medium priority one, the upper car. As contrived as this sounds, it has actually happened in NASA Mars Pathfinder mission where medium priority software takes place, leaving the higher priority software thread. There are two solutions which can actually lead this problem. First is priority inheritance. When a high priority thread needs to acquire a lock held by a low priority thread, the scheduler bumps up and the priority of the blocking thread until the lock is released. Second is priority ceiling, in which a priority called the ceiling is assigned to the mutex. The ceiling is the highest priority of any thread that is expected to hold the mutex. When a thread acquires the mutex, its priority is immediately bumped up to the ceiling value. for the duration that it holds the mutex. Now we will see the solution for heavily contented logs. The first solution comes spreading out contention. In this solution, we create an array of subtables, each with its own log as shown in figure. These can be mapped to the subtables via hashing function. For a given key, a thread can figure out which table is inspected by using a hash function that returns a subtable index. Insertion of a key commences by hashing the key to one of the subtables and then doing the insertion on that subtable while holding the subtable's log. This idea further leads to a connection among multiple logs and which is called fine-grained locking. In fine-grained locking, multiple threads can concurrently access different buckets in parallel. This is straightforward to implement of if the number of buckets is fixed. If the number of buckets has to grow, then the problem becomes more complicated because realizing the array may acquire excluding all but the thread doing the resizing. A reader-writer lock helps to solve this problem. As you can see in this diagram, the table consists of an array descriptor that specifies the array size and location. A reader-writer mutex protects this structure. Each bucket has its own plain mutex protecting it. To access a bucket, a thread acquires two logs, a reader log on the array descriptor and log on the bucket's mutex. How about not using logs at all? Here comes non-blocking algorithms. This algorithm allows us to stop one thread does not prevent rest of the system from making progress. This is a good big achievement. What non-blocking algorithm guarantees us is first obstruction freedom. A thread makes progress as long as there is no connection, no contention, but live lock is possible. Exponential backoff can be used to work around live lock. Second is lock freedom. The system as a whole makes progress. Third is wait freedom. Every thread makes progress even when faced with contention. Very few non-blocking algorithms achieve this. Non-blocking algorithms are immune from log contention, priority inversion, and convoying. Non-blocking algorithms have a lot of advantage, but with these come a new set of problems that needs to be understood. Non-blocking algorithms are based on atomic operations. A trivial non-blocking algorithm is continuing via an interlocked incremental instead of a lock. The interlocked instructions avoid lock overhead and pathologies. The problem of non-blocking algorithm is known as ABA problem. In this problem, an intervening sequence of fetch and op means fetching and operations by other process might change X to B and then back to A. When the original thread executes interlocked compare exchange, it will be as if the other process actions never happened. In ABA, when execution of A, B happens and again A will be pushed up, the processor will never load. The B process has been already executed and this will lead ABA problem. That's why the problem is called ABA. And the solution to ABA problem is to never reuse A. Now we will see thread safe function. Some libraries come in thread safe and some in thread unsafe version. Be sure to use the thread safe version of multi-threaded code. In this example, reference accounted implementation of a string where the issue arises. From the client viewpoint, each object is a separate string object and thus thread should be able to concurrently operate on each object. In the underlying implementation, however, a string object is simply a pointer to a shared object that has a string data and a reference count of the number of string objects that point to it. The implementer should ensure that concurrent access do not corrupt the shared. state. For example, the updates to the reference count should be used atomic operations. Memory issues. A single microprocessor core can execute hundreds of operations in the time it takes to read or write a value in main memory. Programs now are often limited by the memory bottleneck and not for the processor speed. Multi-core processors can exacerbate the problem unless care is taken to conserve memory bandwidth and avoid memory contention. Memory issues are processing is fast but memory access is low. Multiple cores can exacerbate the problem. Specific memory issues, which is bandwidth, working in cache, memory contention, and memory consistency. I will be explaining those in next slide. Bandwidth. To conserve bandwidth, pack data more tightly or move it less frequently between the cores. As you can see in this example, some programming language, when declaring structure in, for example, C++, declares fields in order of the descending size. This strategy tends to minimize the extra padding that the compiler must insert into maintain the alignment requirements. This is you can see an example like how short integer character and pointer are band to increase bandwidth. It has been used differently in second example. Moving data needs cache. Moving data less frequently is more subtle exercise than packing because mainstream programming language do not have explicit command to move data between core and memory. So data movement arises from the way the cores read and write the memory. There are two ways it does, and first is between cores and second is memory and the core. As you can see in this diagram, the cache-friendly code has a fairly straight performance plot, while the cache-unfriendly version running time steps up from one straight line to another when n reaches approximately 10 raised to power 6. So it means the performance increase when the caching is not happening. Memory contention. As we have discussed earlier also, there are two types of memory accesses between core and the main memory, and second type is between two cores. There are two types of data dependencies. Read-write dependency, which is a core writes a cache line and then different core reads it. Write-write dependency is when a core writes a cache line and then different cores writes it. So interaction among these cores, how it happens. First is it consumes bandwidth are avoided when multiple cores only read from cache lines. And third can be avoided by minimizing the shared location. To minimize memory bus traffic, minimize core interactions by minimizing shared location. Hence, the same patterns that tend to reduce log contention also tend to reduce memory traffic because it is the shared state that requires log and generates contention. Letting each thread work on its own local copy of the data and merging the data after all threads are done can be very effective strategy. Now we will see cache related issues. Fault sharing comes under cache related issues. So first we will discuss this. Two separate caches can share a cache line when they both need to read it. But if the line is written in one cache and another cache try to read it, then it must be shipped between caches, even if the location of interest are disjoint. Like two people writing different part of a logbook and the writes are independent, but unless the book can be ripped apart, the writers must pass the book back and forth. The same way, two hardware threads writing to a different location contended for a cache sector to the point where it becomes a ping pong game. As you can see in this example, the ping pong game. There are two threads, each running on a different core. Each thread increments a different location belonging to the same cache line. But because the location belongs to the same cache line, the cores must pass the sector back and forth, access the memory bus. Performance impact you can see in this diagram because of fault sharing, it reduces a lot. Now I will discuss memory consistency. In a sequential program, memory has a well-defined state. This is called sequential consistency. In parallel programs, it all depends upon the viewpoint. That's why it is called relaxed consistency. IA32 approximates sequential consistency because it evolved in the single core age. The virtue is how IA32 preserves legacy software. Two rules covers typical programming. First is relaxation for performance and second is strictness for correctness. This slightly relaxed memory consistency is called processor order. This figure demonstrates the key sequence in Decker's algorithm. Two variables x and y are initially 0. Thread 1 writes x and reads y, and thread 2 writes y and reads x on a sequentially consistent machine. No matter how the reads and writes are interleaved, no more than one of the threads reads a 0. The thread reading the 0 is the one allowed into the exclusion region. On IA32 and just about every other modern processor, both threads might read 0 because the reads might pass the writes and the code behaves as if this you can see in this figure. Figure C shows how make the sequence work by inserting explicit memory fence instruction. The fence keeps the reads from passing the writes. The fence serves to tighten memory ordering when necessary for correctness. The Itanium architecture. It has no legacy software to preserve and thus could afford a cutting-edge relaxed memory model. The model theoretically delivers higher performance than sequential consistency by giving the memory system more freedom of choice. As long as the locks are properly used to avoid race condition, there are no surprises. As you can see in this figure, A shows a simple and practical example where the rules come into play. It shows two threads trying to pass a message via memory. Thread 1 writes a message into variable message and thread 2 reads the message. Synchronization is accomplished via the flag is ready. The writer sets is ready after it writes the message. The reader busy waits for is ready to be set and then reads the message. If the writes or reads are recorded, then thread 2 may read the message before thread 1 is done writing it. Figure B shows how the Itanium architecture may reorder the reads and writes. The solution is to declare the flag is ready as volatile as shown in figure C. Volatile writes are compiled as store with release and volatile reads are compiled as load with acquire. Memory operations are never allowed to move downwards over a release or upwards over an acquire, thus enforcing the necessary orderings. Now we will discuss two common idioms for using shared memory without a lock. First is the animal represents memory operations whose movement is constrained by animal trainers who represents acquire and release fences. The first idiom is message passing. A sender writes some data and then signal a receiver thread that it is ready by modifying a flag location. In the second idiom, it is called memory cage. A memory cage starts with an acquire fence and ends in a release fence. These fences keep any memory operation inside the cage from escaping. It is possible for disjoint cage to become overlapped by instruction of reordering because an acquire that begins a cage can float backward over the releases that ends a previous cage. For similar reasons, trying to fix Decker algorithm with acquiring reads and releasing writes does not fix the problem. The fix needs to stop reads from floating backwards over writes, but acquiring read can nonetheless float backward over releasing writes. Avoiding pipeline stalls. On processors with HT technology, spin waits can be a problem because the spinning thread might consume all the hardware resources. In the worst case, it might starve the thread on which the spinner is waiting. On Platinum 4 processor and later processor, on Pentium 4 processor and later processor, the solution is to insert pause instructions. Data organization for high performance. It is divided into four kinds of locality. First is thread private. These locations are private to a given thread and never shared with other threads. Second is thread shared read only. These locations are shared by multiple threads but never written by those threads. Lookup tables are common example because there are no writes. A hardware thread tends to keep its own copy in cache as long as it fits. Third is exclusive access. These locations are read and written but protected by a lock. Fourth point is Wild West. These locations are read and written by unsynchronized threads. Depending upon the lock implementation, these locations may include the lock objects themselves because by their nature, locks are accessed by unsynchronized threads that the lock will synchronize. A good decomposition favors thread private storage and thread shared read only storage because these have low impact on the bus and do not need synchronization.